Okay, next up, our Polygon Operators Working Group will give you an update. First, James Masters, the group chair, will tell you what the group does and a little bit more about their plans. And next, Dr. Weiland will give us some insight into the technology they're planning to integrate into OAX POP. We hope you enjoyed the presentation, and please come join the working group.
Yeah, so I just have a short update on, just a couple things, an overview on the working group status and some new features and connectivity. So this is just a quick overview for folks who may not be as aware of OAX POP. I just have, like I said, a very quick overview for those folks. I know a lot of others know about it already. But basically, it's a high-speed Polygon manipulation capability that we have integrated into OpenAccess, the OpenAccess API, essentially. And it uses there's a Boost Polygon library. So Boost is an open source set of various, libraries that are useful in general, and this is one of them. This was actually contributed by Intel back in 2008, and once again we picked that up and we made it work with the OpenAccess object types, so the shape, box, point array, and so forth. It contains the basic Boolean logical operators and or XOR and NOT on polygons, along with resizing capabilities and the unified layer model, or ULM, operations as discussed and agreed upon within SI2 in another working group. And so the bottom picture shows a couple of those relationships that are also available. And they're used, at Intel at least. I know that I know there's others using them, but for my speaking on behalf of Intel, we've used this in some OA-based applications that we have, and I've given presentations on that before in SI2 type events. So, okay, and I've shared this previously as well, but again, just to kind of give an idea of performance, because that seems to be and capacity, that seems to be a key question with this. In the upper right, I have a table that shows some analysis that I did against some other libraries that are out there, professional Polygon manipulation libraries or tools. The data is scrambled so that it doesn't show a theme on any given one tool for the data points below, but the data point for the first row, which is OAX POP, is of course consistent there. And it shows that in pretty much most of the categories for the basic Boolean operations on flat shapes, it does pretty well. And it does well on some others as well. It just dips a little bit in performance for the AND operation, for example. We also did some performance analysis within itself, again, using those the basic Boolean operations in that bottom table. The first four columns show the basic AND or XOR and NOT or sub on there. And then it shows the ULM operations after that, which of course those all derive from the primary ones, and so they're going to be slower just by given that fact alone. But yeah, we just did some testing. Like I said, it was about 50 million shapes on two layers, A and B. Layer A and B, so 100 million total shapes on a 6 GB GDS2, and this is the performance that we saw in the upper right corner. The bottom one actually has to do with just random shapes. Timeline. I just wanted to kind of zoom out on where we are. I was actually quite surprised that this has been going on for so long, but we've had this in place. We've been discussing this or had this in place for about 7 years now. So we started with the proof of concept in 2011, started the working group in 2012, and then made a couple releases in 2014 and 2016 respectively. The 2016 release 1.3 was the last one that we did, and because it was pretty much stable and nothing else is really going on, the working group went on hiatus. And then we restarted the working group this year, basically to, on that bottom set of bullets there, basically to expose some connectivity features of Boost Polygon library that we had not looked at before. and we think may be useful. And then also some property merge features. And we also, at the same time, there's been some ideas of, in fact, I have some code that I've used in the past to improve some performance. So we'll probably, while we're in there, help improve the performance in the scripting side of things due to region queries. And maybe address some residual tickets. Again, there were some tickets filed. They weren't necessarily critical, but they've accumulated, and it would be good to clear that out. This is just, I'm not going to focus on this too much because Larg will pick up and go into a lot more detail, but basically there are connectivity features built into the Boost Polygon library, like I mentioned a minute ago. And we believe that based on OAX POP usage with Polygon manipulations, that having these additional features exposed would be very useful in some of the applications that exist. And so the upper right is just a random layout that we drew as part of the working group to try to prove out how this could work. And then the bottom part shows that connectivity graph. Again, Larg will go into detail on that, so I'm not going to really focus on it, other than to mention that this is what we're talking about right now in the working group. I think that may be it. If you want to try one more slide. Yep, that's it.
So I'm talking about the connectivity extraction. So here the agenda, so I will kind of motivate why we might want that, then go in detail. Or not detail, just I fly through the Boost Polygon connectivity extraction, how it works, just go over the working group example we came up with. We'll mention some performance considerations, then also we'll mention the Boost graph, which might also be useful, and then go over an example of how you can extract connectivity. And at last, I will show a complex layout example we got from SI2 where we can do some more meaningful benchmarking other than the little hand-drawn example. Okay, so why would you want connectivity extraction? I mean, there are many reasons. I just put a few in here. Like, it's interesting for net listing. If you want to do anything of your own, you might be interested in net lists. Another good thing is net highlighting, and this was kind of my motivation to play with it, because we had a particular problem where we wanted to see not only drawn layers, but physical layers, so we needed to run Booleans, complex Booleans, and then get real-time highlighting on our layout engine. And that was kind of my test case, and it turned out to be really powerful and possible in real time on medium to size cells. Another application might be a simple open short detection. Let's say you have some nets in there with different labels, so you could see are they shorted or not, or some kind of an LBS. I mean, sure, there are tools on the market, sure, there are, but in case you wanted to do any customization, this all might be helpful. Other applications you could think of, maybe physical property extraction. Let's say you want to do some kind of a resistance extraction, a number of squares. So also here you need a network, but in addition to that, you might need some more complex processing, like a straight skeleton method or Voronoi. But that's all something we can also integrate. It's really not hard to get any kind of library which is out there in the world integrated into OA. Programming language requirements. So everything I'm talking about can be done with C++, and I provided a little example, which if you are in the working group, you will get this, or you got this already. It's full functional, so you can play around with it. But as James mentioned, we want to expose all the connectivity feature within OA's XPOP. And as you might know, scripting languages are just perfect for quick prototyping. It's really easy to use, and get people started is really easy. So as James mentioned, we were evaluating this Boost Polygon connectivity extraction. Why we talk in this work group is that, sure, you can just natively integrate all the functions available or methods available with connectivity extraction, but it kind of doesn't make sense. You want to wrap these so that most of the heavy lifting is done on the C++ side, and another good thing about hiding certain things is we can simplify the usage on OS X POP so that you deal with not the whole, and you will see this later, there is some weird indexing and stuff. I mean, as a user, you don't care about these things. So we could elegantly hide these from you and just give you a function which gives you right back the result you want. In terms of performance, as I mentioned, and you will see later a chart, some applications, of course, require super fast, like in my case, the highlighting. You want something more or less real-time, meaning a user clicks on a polygon and then you want to see everything highlighted right away. Users are not typically willing enough to wait 30 seconds until something pops up. They will click 10 times to see, well, why is it not popping up? So, but my results so far are really good in terms of performance, and yeah. Okay, the Boost connectivity extraction. So Boost provides essentially a class which is called connectivity extraction. This is just a copy of the meaning. So what it essentially does is you dump in some shapes into this function, and it tells you which shapes are overlapping or touching, meaning if these shapes are on different layers, you know, and you have a model behind that, meaning these two layers are connected, meaning a via layer, for instance, and a metal layer, you know that they are connected to each other. So essentially the way this works, you have a pair of layers, you operate in pairs of layers, and then do connectivity extraction on it. You need to use two member functions for that. One is called the insert. So essentially you insert your polygons on these two layers into the connectivity extraction. As a return, and you see here the unsigned int is the return, you get an index back, and the index, coincidentally, is just an index from 0 to however many shapes you have, meaning it just comes back 0, 1, 2, 3, 4, 5. So this is for your own bookkeeping, meaning the first polygon you put in there gets 0, the second one you put in there is 1, and so forth. Now, once all polygons are in there, you call the extract. And extract gives you essentially for whatever you put in there, it returns a simple graph. Graph can be kind of a vector of a set or a vector of a vector, meaning so your shape 0 is connected to shape 1, and your shape 1 is connected to your shape 0. This is kind of what you would get back from the extract. So, as I said, we came up with a weird little example just to see how this works. This example totally doesn't make sense because you have some via layers which don't have metal over them, but it's just for the proof of concept. And you see this little graph here, and I will explain later how you can create something like this automatically using Boost. And in this case, you see we have 5 nets. So we have this big one here. Some isolated things, which is kind of represents this little polygon here, and then some smaller, 3 little smaller things. So it's a very little tiny thing. And I posted an example which runs exactly that example. So I kind of hard-coded some polygons here, and then you can run through the entire process and get the result from every step, and we can do this in real time after the presentation. Okay, performance considerations. We did some tests where we had some cells, just some randomly generated cells. We had between 5 and 80 cells. Each of these cells has roughly 200 polygons, so it scales up from 200 to 1600 polygons, and the insert and the extract, as you see, is more or less linear in time, so your 16,000 polygons run in a fraction of a second. So the insert is a little slower as the extract, so the extract is about 0.1 second here for 16,000 polygons. And this was just not on a high-performance server. It was just a Core i7 older workstation or desktop computer. Now, in addition to using the boost connectivity, I suggested also to use the boost graph, because if you use the boost graph, it enables you to kind of model your entire layout as a graph, meaning you can then run some graph related algorithms, like, for instance, connected components, which would give you automatically what you're looking for, meaning how many nets do I have in this graph, and you can do graph searches, like breadth search, or any other kind of searches which Boost provides. So that's under discussion, how we would integrate Boost Graph into that as well. The functions or the methods I used were adding a vertex. So for every polygon in my original layout, as you see here, all these circles are my vertices. And so I essentially add a vertex for every polygon I have. Then I'm running the Boost graph connectivity, the connectivity extraction, and then I'm adding in the edges. As I said before, you need to do this by layer pairs. So essentially you sort, or the order doesn't matter, you just take a pair of layers which are electrically connected to each other, and dependent on the result of this run, you would add an edge into your graph. There's another helpful function which just checks if there is already an edge, because as I mentioned before, the connectivity extract gives you like I mentioned, there is a connection between node 0 and 1, but you get also a second record which says there is a node between, there's an edge between 1 and 0, so you would get two edges in your graph, which you don't want. So you simply check if there's already an edge in your graph, and then you don't add an additional edge. And then you could run the connected components. That would give you, the result would immediately tell you you have 5 nets in there, and then you can, for each of these, you can list exactly who is connected to whom. And then there is this neat little function called write gravits, which gives you exactly a PNG or SVG, whatever format you prefer to print the graph. It, of course, doesn't make sense for large layouts, but for tiny little things, it's a nice feature for debugging purposes. Okay, so how does this work again? I just quickly, I mean, there are many ways of implementing that, and if we do it in OA script, we would probably do it slightly different, but this is how the example works. So I would read my OA shapes, copy these shapes to Boost polygons, create my Boost graph for each shape I have. So I have n number of nodes in my graph, meaning n number of polygons. Then for each layer pair, as I mentioned, AB, I insert the polygons into the connectivity extraction. I run the connectivity extract, and for the result, I add an edge in my global graph. And I do this for all my layers pairs, and at the very end, I run my connected components. And then I get my result. As I mentioned, SI2 provided a more complex example, which I think is really cool, because that allows us to run some more realistic test cases. So, for instance, we could benchmark just some algorithms we are playing with, just to see how they behave in terms of timing. For instance, you could think of just select a VDE net in here and see how long it takes. So it's a fairly large layout, which I think it's, correct me if I'm wrong, Marshall, it's a 45 nanometer?
Yes, it's an AND-Gate 45 library, which is free as well. So this is not a functional net list, but it's just random logic. So. Yeah. But for our purposes, we don't care whether this functions or not, and whether this, I think this particular example doesn't have any front end, but we don't care about this. It's just a matter of having more realistic placement of polygons instead of having a million random polygons. So this is, I think, a good start. Let me just share quickly. So as I mentioned, we have this, I've built this little example. So I posted that into PowerPoint to the working group. And essentially you will see this is more or less hard-coded. I didn't want to put any open access related stuff in here, just to have a self-contained example, so you don't need any dependencies. So this is just the example we had here, which I
Then in the code, I run the connectivity for the layer pairs, as I said, between, for instance, metal 0 and VR1, and that would be the output. Exactly like this. So it's kind of self-documenting, I hope. If you have any questions, just ping me, and we can discuss details in here. But if you run this example, you see this is just in a fraction of a second. You get all the outputs. Like in our case, we had 5 nets, and here's exactly what is connected to each other, and that would be your result. So it's probably a good start if you want to play around with the whole connectivity, boost connectivity and boost graph. So that's pretty much what I have.